It's working, right? So I'll continue the lectures. We were looking at some stochastic PDE, right? And before I start, I have been saying this can be done by a Grunwald argument and so on. So Grunwald lemma is very important, huh? And everybody likes it. So I'll first state it here. Maybe you can help me. So this is Grunwald lemma or Bellman-Grunwald lemma, whatever you call it. Let's take not the most general case, but reasonably good enough for us. Let's say these are L1. We can take it to be 0 to t. Pardon?
The microphone, I think, doesn't work.
It doesn't work, huh?
We can move it up, or you may want to put it closer.
Yeah, it's probably
Maybe too low.
above. Okay, this is better. Okay, I can also shout if I want to and be very loud. If f and g are L1 of 0t, and let's say f of t is less than or equal to g of t plus c times integral 0 to t f of s ds for all t in 0, 1. Then, what is the conclusion? C is some positive number, let's say, right? Or negative, whatever. Then help me out. F of t is less than or equal to? Right. Okay, I'll write first the integral form since they seem to know, and then, yeah.
G of t. Integral.
CT.
T minus s times g of s, huh? Should be multiplication. Why? Suppose I take g of t to be g, let's say, constant. What do I get here? I'll get a g times. So let's examine, right? G times e to the ct is there, and then I have e to the minus cs, which I can integrate, right? So the one g times. Am I doing things all right? 1 minus e to the minus ct. E to the minus ct and e to the ct cancel out, right? So what do I get? G times e to the ct divided by c minus, and they cancel out, I get a g over c, huh? Am I right? Okay. And here I have a g, right? G of t is g. So what has happened now? So how does it all cancel out? There is no constant term here, huh? Okay. All right. Is there a C also here? No. Okay. There is a C, right? All right. So if there is a C, which there should be, then I have this also, right? And then if I have a C, okay, so the C's cancel out. So in order to get it to be G times e to the minus Ct, I have a subtraction by G, so I should also have an addition by G. So I have to do these carefully. Right. So what I wrote is correct. So I'll write here, if G of t is just a constant G, then f of t is less than or equal to, so this G went away, so I am getting G times e to the Ct. This is how we would all be using it in the simplest case. So there is nothing wrong there. Okay. And it can be generalized and so on. It doesn't have to be just a ds. There could be a d mu of s, in which case I'll have the measure of the interval s to t there. Okay. So that's called grown volume. So there is a G of t. Okay. So you all know this, right? I wrote it in one form. That's useful for me, initially at least. So now let's get back to our equation. Derivative of u with respect to t plus, no, there is no plus right now. Where was the au? It was all on the right hand side. au plus f of u. So when I write au and u and all that, it is u of t, right? F of u of t plus sigma we were considering this on a separable Hilbert space H. And u of 0 is given to us. U sub 0. See, once again, going back here. If C is actually 0, you won't get anything here, right? But then F is less than or equal to G, so you need this G. Otherwise, you'll be in trouble. So we considered the solutions in the mild form, and then we showed that it is Strong-Feller. Correct? The Strong-Feller argument was kind of maybe, for some of you who haven't seen the Ito formula, for instance, it would have been a bit rough, right? But I guess you all saw the Ito formula in the last lecture, right? So I don't have to repeat. So that's done with. Today we will just do irreducibility. Okay. What does irreducibility mean? Supposing I start at some place, say z1, so u of t, z1. Right. That means that I am putting the starting location. Instead of u sub 0, consider it as z1. And that should come arbitrarily close to some other point z2 in the Hilbert space. So the probability or the absolute value of this, okay, being less than epsilon should be greater than 0. That's what we want to show. Correct? So let's consider another equation. Derivative of x with respect to t equal to ax. You can put the little t's and all that. Okay? Plus f of x of t. Instead of putting the sigma dw, let's just put some control term. All right? Where, let's say, x of 0 can be at some z1. Then we can call this as It can even be any z, for instance. Call this solution as x of t z theta. Now, where is theta? Theta is in L2 of 0t h. Let me also put a capital T here. Maybe we are given a capital T, arbitrary, and right at that time we had to come very close to z2. So here I can also say where z1 and z2 are, right? Let me make amends for it by writing z1 and z2 member of H. Okay, so this is a controlled PDE, and it's well known that this is approximately controllable. What does that mean? The process X, T theta, T Z theta is approximately controllable. What does that mean? That is, given Z1 and Z2 member of H, any x of t Z1, okay, given Z1, Z2 member of H and t greater than 0, there exists a theta which is in L2 of 0t h such that x of t z1 theta comes close to z2 there exists and epsilon also has to be given.
What was the condition on sigma?
Good question. The range of sigma has to be dense in H. So I'm going to write here is approximately controllable. Here, range of sigma is dense in H. The proof is actually by Grunwald inequalities and stuff like that. So it's longish, but then you don't learn much from it. Okay, so I'm going to skip that. Why do I skip this statement? There's actually a theorem. I'm skipping it because there is no DWT, and if there is no DWT, I'm not interested. Huh? Okay. So here, now I will prove that my original process is irreducible. Do you all understand? So this is a theorem. If you want to, I can write up a proof of this, but then that would be longish and I won't be able to say much of other things. Okay. Now the theorem we want to show quickly is that U of T, Z, these kind of processes, right? So this is the starting point, okay, is irreducible. Provided this hypothesis is true under this hypothesis and all other prevailing hypotheses under this additional. What is the hypothesis? That's right there, right? Yeah, I didn't write it as under the above hypothesis, then you won't know where to look at. Under and above, and you'll get confused. Proof. So this is the statement we want to show, right? And here there is a process here which is deterministic, and we know that under this condition it's approximately controllable. I take that for granted. So instead of showing this, I can also show the following. Probability of absolute value of U of t, Z1 minus Z2 is, let's say, greater than epsilon, greater than or equal to epsilon, less than 1. So this statement and this are equivalent, yeah? because what did I do? I just took the complement of the set and therefore the inequality reversed, right? Okay, now let's consider absolute value of u of t z1 minus z2. Are you all with me so far? Nothing much has happened, yeah? Any questions? So this is less than or equal to u of t z1 minus, I'm going to intercede it with this x process, x of t z1 theta plus x of t z1 theta minus z2. Anyone has a problem with this? Nothing. So just triangle inequality. And now I'll choose my theta such that the second quantity is less than epsilon over 2. Because it's, I said it's approximately controllable. Therefore, given any epsilon greater than 0, right, I'm guaranteed of the existence of a theta, which would make it small.
Where did you get this approximation probability result? What's the reference?
The Prato.
F is a bounded Lipschitz function.
F is Lipschitz continuous. Yeah, F is just Lipschitz continuous with globally Lipschitz. Yeah, with a constant C or whatever as the Lipschitz constant. Yeah, it can go up to linear growth. Right? Yeah. So choose theta. Such that second term on the right side is less than epsilon over 2. That's possible, yeah? But then this whole thing has got to be greater than epsilon, right? That's what we want, okay? This needs to be shown. We don't know it. So I just wrote an equivalent statement for irreducibility. And therefore, the first term has got to be greater than or equal to epsilon over 2, correct? Therefore, you all understand? We want this, right? That's what we want. But then I broke it up like this. If this is going to be less than epsilon over 2, and if this is also less than epsilon over 2, then we are cooked. The whole thing would be less than epsilon, but we want it to be greater than epsilon, right? So we need to show that probability u of t z1 minus x of t z1 theta. What did I say? Greater than or equal to epsilon over 2 is less than. That's what we need to show, correct? So consider this difference then. So stop me if you have any questions, okay? Both are starting at z1, so the initial part is gone. Yeah.
One request.
All right. Bigger. Okay. Sure. Increase the font size. So first part is gone. What else is left out? We had an A and an F, correct? To begin with. So we have integral, maybe I'll just consider first a little t. All right? E to the t minus s, A. And then I'll have f of u, right, of s z1. And what will I have here? Will I have a corresponding term in the other little x part? I'll have, right? Because that there also I get a capital F. So I might as well write them all together. And f of x of s z1 theta, okay, ds. And then what else am I left with? There is this stochastic convolution integral, which I can call as zt. That's what we have been calling it. And then there is going to be a minus integral 0 to t e to the t minus s a. What else is there? Theta of s, right? So since I put absolute value everywhere, it becomes an inequality. All with me so far? And this is going to be less than or equal to. Now, under the assumptions that we have on f and so on, f and a, there is going to be a constant times integral 0 to t of the absolute value of exactly what we have in the left hand side, on the left hand side. And we have x of s, z1 theta ds. And then what else will we have? I'll just call this as some ht, okay, this whole integral. So I'll just write it as zt minus ht. Now I'll apply the Grunwald lemma, all right, with the little g identified with z minus h in absolute value. So, what does the Grunwald lemma say? Now it doesn't matter what font size I use. Z1 theta is less than or equal to what?
CT minus HT.
First of all, I'll get the zt minus ht, right? Plus integral 0 to t e to the t minus s a. No, I don't have a and all that. E to the t minus s k. Yeah? Oh, k times e to the t minus s k, and then what else? zs minus hs. It has to come out to be a convolution term. Okay. Therefore, we want this to be greater than or equal to epsilon over 2, which means this has to be greater than or equal to epsilon over 2. And notice that z, we have already proved, has a non-degenerate Gaussian distribution. What is h? I just called it by capital letter, but it's actually a deterministic quantity. All right. So we are talking about a normal random variable, right? So this is just the deviation of an absolute deviation of a normal random variable from a deterministic value, and the same things are here as well. You can bound all these, right? So that's not a problem. Okay. So we are only looking at 0 to capital T. So probability of the left hand side greater than or equal to epsilon over 2, right? It would be greater than or equal to epsilon over 2 if this side is greater than or equal to epsilon over 2, right? You understand? So this is what we were trying to compute, but that all comes out to be as to whether, okay, if this is greater than or equal to epsilon over 2, this is automatically greater than or equal to epsilon over 2, right? And as I told you, these all can be replaced by some k1, right? You can have k1 integral 0 to t Therefore, what is the probability? You all understand what's happening? I wanted this to be greater than or equal to epsilon over 2, right? That would imply that this is greater than or equal to, right? Implies relation is mathematical logic notation, right? And in set theory, it would correspond to subset. Therefore, I am going to say that the superset actually has probability less than 1, which would mean that the subset also has probability less than 1. Understood? Therefore, so now I want it only at capital T, right? Because that's what we wanted. And this, of course, has probability less than 1 because a Gaussian measure has support everywhere, right? If you want to, you can even make this even larger by putting the L2 norm, right? You can put the 2 here. How do you bring a 2 there? If there is no 2 to begin with, how do you make it as a 2? Yeah, Hölder's inequality or Jensen or whatever, in which case you got to put, there is a toll to be paid. You have to put a capital T here, right? So it's not a big deal. So we know that this is less than 1 since Z has non-degenerate. Gaussian. We have seen these before. So any epsilon ball will be charged by this Gaussian random variable, even if you take the deviation from it by a constant, correct? And that's the idea. So we are done with irreducibility. Okay. So I just wanted to show you at least Strong-Feller and irreducibility. Now you got to also know that there exists an invariant measure. I have given the ideas for choosing an invariant measure. It doesn't automatically, just like that pop-up, you got to do some more ground wall arguments, all right? And I will skip those, it will be in my notes. So let's say that this model is done for. I just wanted to show you the 2 sufficient conditions that are essential for proving ergodicity. So you got to put together all these hypotheses carefully. Call it as hypothesis H. If it's painful to call it by, say, assumptions 1, 2, 3, 4, 5, if you don't want to list them, call them all as hypothesis H and everybody's happy. So there is one more hypothesis here that range of sigma has to be dense in H. Okay, so since null controllability and approximate controllability were discussed here, right from the first week, I thought I would connect it. Professor Sridharan actually last time itself said, oh, the irreducibility it should correspond to controllability issues, right? Of course it does. Okay. So we started with the Doops theorem, right, which gave us conditions which are verifiable, as you can see from these 2 examples, namely the linear equation and the nonlinear equation with the Lifschitz nonlinearity here, right? So those are the 2 simple examples that illustrate the power of the Doops theorem.
So when you prove the Strong-Feller, I forgot, did you assume non-degeneracy in noise?
Yeah, that's right. Sigma inverse has to be a continuous operator as well. Yeah, it has to exist and be a bounded operator.
So this is the whole picture is for non-degenerate noise.
That's right. Right. That's right.
Degenerate noise, right?
Correct.
Because
non-degenerate noise. Yeah.
Controllability requires.
Correct. Yeah.
These are abstract controllability theorems, but there is so maybe it should help get a precise reference on who proved this.
That's right. That's right. Yeah. So you can look at the Pratos. Here's a beautiful book recently on Kolmogorov equations. I'll write down the exact references. And his paper is also very good. And maybe one should go to the paper so that you see the power of the techniques.
If this is accurate, it's probably proved by either Fatterini or Russell or something.
Okay. Oh, it may go back to them. Yeah. Yeah.
It is their theorem.
I see.
So
Yeah.
Fatterini is probably good.
Okay. Yeah. But the proof itself is quite simple. And that's why I skipped that deterministic issue. So now we'll come to Navier-Stokes equations. Again, I'll just say something that's easily said, okay? Not the most optimal conditions and so on, because those are like icing on the cake. Namely, you can always change them, make them to your taste. So you are all experts now on Navier-Stokes equations, aren't you? So I should be scared to talk to you all. So we'll consider the two-dimensional Navier-Stokes. So what is the equation? The original Navier-Stokes equation will be what? Laplacian of u. What to put on the right hand side? Gradient of p in G, let's say, subset of R2, open connected domain with a smooth boundary and so on, correct? So that normal can be defined, stuff like that. And then is that all? So here U stands for what? Velocity, and there are two U1, U2, right? So it's a two-dimensional equation, and then the divergence is 0. Is that all? Initial condition, very good. Let's call it as U sub 0 of x. Boundary condition is what? Let's call the boundary as gamma 0. Very good. So this is the Navier-Stokes equation, and how do you write it in using operators? First, we don't know where to post this maybe, so you build some spaces. V is, let's say, C0 infinity functions, right? C0, so there are two components again, right? So any element will be V1 and V2 also, right? C0 infinity functions with what? Divergence equal to 0. And then close this V, right? The closure of V in the L2 of G norm will give you H, right? Called H. The closure of V in what other norm can we say? In W12 norm, right? Or any alpha for that matter. W alpha 2 of G would be what? We can call it as V alpha, correct? So then what is the triplet that we get? I'm trying to see. That has to be proved, right? Oh, the characterization of H. The characterization of H as L2 functions with divergence equal to 0 in the distribution sense, and U dot n equal to 0, that will, you have to prove it, right? Yeah. You can see the proof in Tamam's book on Navier-Stokes Equations, theory and numerical. Numerical what? And numerical. Those are two different books. Yeah.
Ask the question louder.
Yeah. Oh, I have to ask the question louder?
No, these guys.
Oh, I see. Yeah, they are answering me, and they are giving so many references. So I can see your influence there. And, okay, so what is the triplet that we get? V is then contained in H. So this is the embedding that we start with, right? Okay, where V denotes actually V1. Okay. And you can define, instead of putting a minus nu Laplacian and so on, right? If you restrict your U to functions which are divergence free, then you get an operator, right? And by Rie's representation theorem, but then you all know that. Huh? Oh, V1 is when alpha is 1. So one's differentiable functions, right, in the Sobolev sense. Okay, so what was I saying? Oh, Stokes operator. Oh, this prime, V prime or V dash, that's the dual of V. And already I think you were told that H, and you can identify it with H prime, right? And so on and so forth. And also you cannot identify everything with everything else. You won't get this inclusion, right? That was also mentioned. Very important point there. And the norm here, we'll just call it like this, and the inner product like this. The norm here will be like this. And the inner product, I will just say that it is the V inner product, okay? And likewise for V prime. If there is a V prime norm, I'll put a sub V prime, okay. So if you project this equation to divergence free vector fields, then the gradient of P will be 0 because it lies in the orthogonal complement of this projection, right? And therefore, in the operator or evolution equation setup, the equation would become plus nu times AU, where A is the Stokes operator. You have seen it now for 2 or 3 days, right? Actively, you have seen it. Maybe for many more days, actually, for a week. And then this is the inertial term, so to say, or the nonlinear term, and that can be, that's a trilinear form, therefore there is a bilinear operator, and you will get all these things, and this becomes 0. So since you have projected everything to divergence free vector fields, there is no reason to say this. Then U of 0 is U0. Let's say now I can write a member of H and all that, correct? And U on the boundary. Or I don't even have to say that because it's all built in this function space, right? So this is the equation that we want to solve. Any questions? Did I go too fast? Or should I say more? I can say a lot more. So this A is the Stokes operator, and the Stokes operator is self-adjoint positive, right? And it has a compact resolvent. What is a resolvent? What is a resolvent? So A is an unbounded operator, right? That you were all told. And the resolvent also was discussed. A
Lambda minus A
inverse, right? Yeah, very good. A minus lambda I inverse, that would be the resolvent. And it's compact, therefore the spectral theorem applies, and therefore what? It has, in terms of eigenvectors and eigenvalues, you know it, right? So let's write down a few things. So there exists A Ej equal to lambda j Ej, right? 0 less than lambda 1 less than lambda 2. And Ej's form a complete orthonormal basis in H. I don't want to say too much because I need time to discuss invariant measures. So that's why, on the other hand, I don't want to rush through this. What is this B? I'll just recall, right? It's good to see some things, sometimes a couple of things, a couple of times, yeah? So I hope you don't mind. So how do I get the B of U? I look at this. I have U dot del U, and then if I take the inner product with respect to V, some other function, right? Maybe I'll put first something more general. This is u and u. If I put a v and a w, so this inner product simply means, right? What does it mean? It's the L2 inner product. So you have and then apply. So there are three functions here. Of course, I is repeated, j is repeated. So we use, there is a summation also over I and j, but just goes from 1 to 2. And call this as b of u v w. And absolute value of b of u v w by what is it? By the Helder inequality, give it to the power 4 here, 4 and then 2, because 1/2 plus 1 over 4 plus 1 over 4 is 1. And you will get norm u L4 of g when I write, huh? All right? And there are two components, therefore you have to take each to the power 4, right? Times. This is the derivative, so it will become del v L2 and then w L4. That's just Helder's inequality. And then simply make use of the fact that w12 is in L4. Correct? Therefore, you can put instead of the L4. So whenever there is an embedding, the sign is used when the norm here can be bounded by the norm here. All right? So you can then bound it by norm u half. I'll just call it as half. It can also be called as h half, right? And then I have norm v. If there is this is the Dirichlet integral, and therefore it would be the v norm. Norm of w half. And then simply make use of half is sitting right in between 0 and 1, therefore use the interpolation, and you'll get things like this. And then the same thing comes here also, right? So when I just put an absolute value sign, you know that it is the L2. So this is like it has the L2 of G norm, right? And also here there is a, I didn't write fully. I got to put to the power half. Huh? Okay. So I'll just take a couple of more minutes to say about Navier-Stokes equations, and then we'll get to our problem. Now this b of u v w. Okay, what has happened here is let me make u and v to be the same. Because that's what we want here. U, and then I'm hitting it against a W, right? This would become what? Okay. First of all, I had to say this. No. You do an integration by parts here, and then make use of the fact that everything is divergence free. You do this for nice enough functions. Then you can write this as negative b of u w u. Therefore, equal. So if u and w are the first and the last are the same, you can pull together the to the power half and all that. So you have this. And then I'll just have the W. When I put double upright here, that means it's the V norm, right? So when I have a single one, that's the H norm. And that's it. Therefore, this holds for all W. Therefore, we get the following inequality. Maybe there is when we apply all these embedding and all that, there is at least a square root of 2 here. I'll just call it as a 2. Okay. 2. Not a big deal. I just want to be So this holds for all W, and therefore the V prime norm is less than or equal to 2 times absolute U. Square root of 2, but then I put a 2 because certainly it's true then.
Because you first take an L4 norm, right?
That's right. That's right. Oh, it may depend on G, right?
Yeah. So it will be just the C is good. After
C.
the first step, yeah, just the C.
All right. C. All right. I just wanted to reserve the C for later use. It comes in handy. So this is what we mean by saying that in 2 dimensions, in the Navier-Stokes equations, the nonlinear term is quadratic in growth, right? Quadratic because it is not just bounded by something like this or like this, C times one of the norms, but it is really both the norms play. Right? Okay, so anyway, this is what we call as B of U, right? Here it's a trilinear form, therefore there is a bilinear operator going from there exists a B from V prime to V cross V, let's say, right? V cross V to V prime, such that all these hold. That's the inertial term. So that's that term. Okay, we will make use of all these bounds and so on in some way. So this is a short introduction to what you already know, namely the Navier-Stokes equations. We are considering only 2 dimensions so that there is solvability. Now what shall we do? So what is the abstract equation? I thought I wrote somewhere derivative of u with respect to t plus au plus b of u equal to 0, and u of 0 is some u sub 0 method of h, right? The 0 on the right hand side is not so nice. We want to put some forcing term so that we can talk about invariant measures. So I'm going to put the easiest of things because we don't have to be too clever in putting a noise term, because that's mathematically nice if you can prove something in more generality, but who knows how the noise is. You have to model, right? And modeling of the noise is hard. So we'll stipulate that there is a sigma, which sigma of t, let's say, sigma 1 of t. You don't even need the dependence on t, okay? Sigma 2 of t, member of L2 of h. All right? That means it takes values in L2 of h. The little L2 means it's a sequence space such that the sequence is square summable, correct? And each is h valued, right? Do you want me to write down the definition of L2, little L2? No. So it simply means nothing random there. So write down, let W be also W1 of t, W2 of t. Wj's are identical, independent copies of a standard Brownian motion. Real, standard real Brownian motion. If sigma is an L2 of 0t, little L2 of h. That is, it's square integrable, right? With respect to when you hit it with an integral from 0 to t, then integral of sigma dw, sigma of s dw from 0 to t makes sense. And lies in h. And is h value. Therefore, let's put this on the right hand side. Why make a big fuss about what is it, trace operator and this and that, right? So how about that? So when you write it in the stochastic integral sense, it is just this integral. Let's see what happens. So in what sense? So now the stochastic integral itself has a meaning, therefore we need not go for the mild solution. We can just talk about the weak solution. So how do we want the solution to be interpreted? So let's call this, I already called some things as 1 and 2. So solution of 3 is the following equality, namely u of t, v, okay, so you got to hit it against a v, and then au, because A takes values, it maps things from U to from H to V prime, right? So this is called the dual pairing. Do you all know what is dual pairing? And then I had to integrate it because I didn't write it in the differential form. Everything okay? Plus integral 0 to t. So dual pairing simply means that you have something that takes values in V prime, okay? Let's say, what shall we call the V prime thing to be? Some z, lowercase z, and then some v. So this guy is in V prime, this is in V, okay? In which case, it's not, it's called the dual pairing between V prime and V. So the action of V prime, this z on V. Okay. That's all we can do because A maps from V to V prime, right? H to V prime. B of U to V prime. And B of U, B, ds. There is also a U of S here, okay, equals. I have all these things. What should I put here? Sigma dw is there, so I had to hit sigma against this B, right? Sigma j, let me just make it all easier. So sigma j, comma B, yes, sigma j. For all B, correct? There is a U0. Okay, I didn't put everything, yeah, this side I'll put a U0. Thank you. Yeah? Which term? New. No, I didn't take it to be 1, so it should be here. Very good point. Some of us miss it when we write, when we type and so on, but it's important. So this is called the weak solution. when you hit it against a test function and then look at the, say that you want this equality, then it is called a weak solution. All right. Now, theorem. I don't care to prove solvability because solvability was already probably done using Galerkin approximations, monotonicity, Minty-Browder, and so on, right? You know that probably. And so we can get the following. Let U0 be in LP. Omega H. And sigma be in some LP of omega L2 of H. That's not enough. Omega cross 0 T. I'll call it as omega T, where omega T is actually omega cross, well, there is no need to define all this, just 0 to T, because I said it's not random, right? For P greater than or equal to 6. Then there exists a unique solution. Yeah, in this sense. A solution of 3 such that U actually has very nice properties. Okay, L4 of G cross 0 to T. What else is there? G cross 0 to T, that's it, right? Cross omega. Because it's a random process, right? So I got to put omega, it's a process, therefore there is time also, and then there is it's also spatial, therefore G is there. Intersection, L2 of 0 T G, I should also put omega, right? Here. Intersection LP of omega, you cannot read this, right? If I write it there, I'll write it on the other side of the board. Oh, we don't need this anymore, right? We are all convinced of the truthfulness of this? Yeah, okay. Huh? Yeah, you don't have to take it to be deterministic. Yeah. You can, but not necessary for the solvability theorem. And then it is in LP of omega cross 0 to T omega C to 0 T H. And the solution is pathwise unique. This is a theorem proved by Menaldi and Sridharan. Using Galerkin approximations. There is not monotonicity, but there is local monotonicity on bounded L4 balls in V, whatever that means, right? I'm not going to go into that because my job is not to prove solvability. I had to show the properties of invariant measure, right? Or existence, uniqueness of invariant measures. And the solution is pathwise unique. Okay, so that's it. Now we come to the last part of today's thing. I have 30 more minutes. What? P is greater than or equal to 6. You need at least 4, I think. Yeah, I looked at it, right? But it's all right. Let me just take it with 6. It's safer. So we are not looking for finer properties. We want to get the big idea, right? Under some conditions there is solvability. Now let's look at the properties, right? So how long to just say existence and uniqueness, though that's the crux of the matter, right? So now a theorem. Let U0 V0. Now I'm going to just take members of H. So you don't have to worry about this P, at least here, right? Let visit as T, I can even say it like this. I'll just make it all bounded. Finite quantity for all T. So let's say a bounded jump. In fact, I'm going to make it even worse. Okay? If a mysterious condition will be here. If nu cubed, what is nu? It's our viscosity constant. So far nothing has happened. You got to just know that this is so, because I think Professor Sridharan will tell you more about solvability of the stochastic Navier-Stokes, right? If you have time, okay. Since he would be the right person to say that. First eigenvalue. Of the operator A. It's a positive number. Then I'm starting at two different places and I want to find out this difference between the two. And that would come out to be 0. And this equality goes exponentially fast, okay? Okay. In time. Of course, in time, because it is time that's going to infinity. So this is like showing that the random dynamical system has an attractor. It's a stochastic dynamical system because there is a noise. Okay, this kind of a theorem would be called exponential stability. Almost sure, yeah, almost sure. So if we have such a statement, then we can expect an invariant measure, because things are at least asymptotically, right? They do not depend on the initial conditions. That's an important thing. And this is an almost sure statement.
So again, can you write down what equation you are considering?
Oh, this equation, equation 3. So I have all the conditions of the solvability, but then this condition actually drops out because I'm just moving from a fixed point, h, right? It is not random. I expect sigma to be at least in L4, I just wrote it as L6. So notice that nu is supposed to be small, right? Because it's a viscosity coefficient. If it is too large, it's the flow is going to be like honey or something, right? Too viscous. So it's not so interesting. L is my bound for the noise. So I'm only looking at the small noise. But that's because I want to study large deviation principle for invariant measures under small noise as the smallness goes to 0. That's called the small noise asymptotics for invariant measures. Okay. So that's a paper that will appear, and so I'm not bothered one bit that it is small noise. Okay. You can also do better things if you want. Yeah.
So what can we say about the difference between U0 and V0?
Oh, U0 and V0, they are just anywhere. nothing at all. They are anywhere in the space. But as time goes to infinity, there is a unique attractor, probably, right? That's the idea. And it's going exponentially fast in time. Okay. So the proof itself is quite simple. So let's write down the equation solved by this. U of t u0 minus, instead of calling this as u again, maybe we'll call it as v. Any problem there? Because it corresponds to v0, it's nicer. So then I don't even have to put the u and the v, because u and v are the solutions with initial condition u0 and v0. So I can make it all look even nicer. Consider this. This is an additive noise and therefore it drops out when you take the difference. Therefore it is just going to be u0 minus v0 plus integral 0 to t. I'm just writing this so that all of us are together in this venture. Plus b of u s minus b of v of s. Yes. I'm just writing it as though I don't try to hit it against anything because I solved it in the strong sense. Plus, that's it. Because that's the nice thing about additive noise. And for a long time, even now, I think additive noise is not to my liking because the stochastic analysis drops out, right, somewhat. But that's okay. It makes life simpler. So sometimes you have to care about life. So what is the energy equality? Energy equality is like applying the Ito formula here, right, for the energy, right? So you take the H norm squared. So it's not that simple though, right? So you want it larger? Okay. And that's less than or equal to, shall we give a name for u and v? U minus v, let's call it as w. Then it's easier for me to write. W is, let's say, u minus v. Then w of t squared is w of 0 squared 2 nu integral 0 to t. Can anyone tell me what happens? You would have seen this in Professor Sridharan's lectures. So it is AW, right? So W of t is there. I just took the inner product with W of t. But then you had to worry about, right, just as in the Ito formula, first derivative, second derivative, and so on. Okay, so it will become, first let me write down. Maybe this is easier. So it is like taking the inner product, let's say. The 2 came in here because of taking a derivative. And the same thing here also, right? 2 times what? B of u minus B of v. Comma W of s, right? That's it. So if you work with this, okay, first of all, what happens to this? You can put a to the half, and you know that the a to the half norm is equivalent to the v norm, right? So you can write this as W of 0 squared plus 2 nu integral 0 to t. I can put now the V norm of W of s squared ds plus, now let's come to this part. Before we fill it out, of course I can always put this. I don't know what to write here, right? So what is this B of u hitting W, right? Do you all remember it's, you have to go to its grandfather, right? Namely, it all arose from here, right? So this is, let's subtract the u v w maybe, and then put b of u v w. I just subtracted and added something, right? And this is b of u. It's trilinear, therefore I can subtract the u minus v. Are you all with me? Plus b of u v w, correct? So u minus v has another name w, so it is w w, therefore it's 0, correct? So this is w. You all know that, right? B of the little b of u w w is 0. Recall what was done earlier, right? And therefore that's gone. Therefore this is just a b of u v w. And then what else happens? So I have the b of u. I can replace it by b of u v w, but I have here b of v v w, right? So let me write down. Therefore, b of u u w minus b of v v w is, we found it to be this, right? B of u v w minus b of v v w. B of, now I can subtract the first coordinates because it's trilinear, right? The other two are fixed, have to be fixed. So then you get a u minus v, therefore it is w v w. Okay. Okay. So that's what you will get here. So let's call that as an observation. And so what do I need to put here? Okay, keep that as it is. Right now it is fine. And now let's estimate all these things. So for now you can just put the same thing here. And then I just observed all these. And b of w v w, how can you bound it? Just now we did. If the first and last are the same, you got to put a h norm of w, v norm of w. That was the growth, remember? And then you have some this v. That should be in the v norm as well, correct? Therefore, when you try to write an inequality, what happens? You can take the absolute value there and then put all these things here, correct? So maybe I'll make it as an inequality. This is correct, okay? And here I'm going to put an absolute value and then make it all bounded by this. Otherwise, I won't have time to say everything. Like that. Very good. Now let's look at, there was also a constant which I called as 2, right? Let's just pretend it's 2. So otherwise, I had to put a c and so on, and then explain what it is. So to be consistent, I'll just put a 4 there. And now, Do you all see I made a mistake? Yeah. Sine. Because I have it all on the right hand side, yeah? Usually I have this term on the left side. So there has to be a minus sign there. Huh? Because it was all to begin with on the left side. So if you bring it to the right side, it should become like that. Otherwise, I'm in trouble. And here also there is everywhere W of S and so on. Are you all with me so far? This term also was on the left side, right? I should have put a minus sign here also, but that's okay. I just make it all as. I don't penalize it. Because I know the absolute value, therefore whether it's plus sign or minus sign, I'll get this bound and I put this bound. Got it? Okay, so here what I'm going to do is, if you got two numbers a, b, you know that it is less than or equal to a squared over 2 plus b squared over 2, right? If you want to give less weight to a and more weight correspondingly to b, right, that can also be done. So the epsilon can be, you can put a square root of epsilon a, the same ab I'm going to write, okay, b divided by square root of epsilon. So epsilon, square root of epsilons cancel, so what I have is ab, right, okay. But then this can be thought of as one entity and this as another entity. Then it is like multiplying two numbers. What did we learn here? You had to square the given numbers and put one in either side, in each term, and then divide by 2. So it will become epsilon a over 2, and then c squared over what? 2 epsilon. So that means this a squared is given a very small weight, and correspondingly the b has got more weight. So we will make use of this in splitting this term. So how do we use it in our case? Maybe I can go to the whiteboard here. That's empty. So I have this 4 times absolute W of S. Okay. Maybe I'll first write the V norm and then this, and then I have the V. So I'll take this and make it as, that's one term. If I want, I'll write the same thing as follows. See whether it's all correct. I'll put a square root of 2 divided by square root of nu. This is not the most optimal or anything. I'm not looking for optimality, right? And then 4, I get divided by some things and so on. So I'll put a square root of 2 here and a square root of nu. All right? Here I just have a 2 nu, square root of 2 nu, and here I have a square root of nu. Right? So the square root of nu's cancel, square root of 2 also cancels. So I haven't changed anything here. So I can return this and W of S and then norm of V of S. So I treat this as one entity and this as another entity. Therefore, it will become less than or equal to 2 nu norm W of S squared divided by 2 plus, can anyone tell me what else happens? So I'm applying exactly this, yeah? So should I square everything? I have to square all the remaining things and divide by 2, that's all, right? Okay, 4 squared and divided by 2 nu, and then I'd also get another 1/2. 2 and 2 cancel with a 4, so I get a 4 over nu times these guys. Okay, W of S. squared and this will be 2 and 2 cancel out, I just get a new. Correct? So if I split this term in this way, then I'll get a nu times the square of the V norm of W squared. That can be cancelled with one of these nu's because I have minus 2 nu waiting here, right? Okay, therefore. So what do I get now? Sorry. I hope it's erasable, right? W of t squared is less than or equal to W0 squared plus, well, I'll put this plus nu on the right hand side, left hand side. So out of the 2 nu, 1 nu has gone away because of this, right? In order to accommodate this term, I can cancel partially with this and then I take it also to the other side because it's annoying me. And then the other things are 4 over nu. I had W0 squared. Plus, what did I say? 4 over nu, integral 0 to t. So it's not just W squared, there is also the norm of V squared. Over nu, what did I say? Yeah. W of s squared, norm of V of s. I haven't taken expectation and all that anywhere. It's all almost everywhere, almost sure. Therefore, does what is the theorem called? Grunwald lemma. Does it apply? Okay, tell me correctly, because. Tell me, so because you know that I'm not so strong on Grunwald lemma, right? Huh? Yeah, tell me. W of 0 squared. Huh? W of 0 squared. No, that's not depending on time. I needed that for the previous case, right? Namely for proving irreducibility. But here it's just a constant. And then what? There is no integral and all that. See, you have to see this as an equality. I'll tell you what happens. Yeah. Oh, this is yeah, that's correct. You have to see this as an equality and then solve the. These are all the linear parts. This is not so linear. Maybe there is something multiplied. That's okay. And you know how to write these the convolution integrals. That's all there is to it. So I got W0 squared and then what else here? Exponential. Exponential of what?
Over nu.
Integral 0 to t, yeah? Okay. V of s squared minus, it is also a nu, right? Yeah, ds. Oh, maybe you want to write it this way. Because there is also something left over there, right? Yeah. Which one?
The integral can be the half, then W of t square is just bounded by this.
Oh, I see. Because it has the double norm, right? Okay. The double norm can be bounded by lambda 1 times the single norm. Why? Because lambda 1 is the first eigenvalue, right? Therefore, this will be Poincare inequality. You all remember that, right? Professor Sridharan emphasized this inequality, if I recall. Didn't he? Yeah. So you can use that and then maybe make it as new lambda 1. Very good. Now what is it that we were wanting to prove? Sometimes you know that happens, right? When you are proving something, very often in initial stages, we would take the left-hand side and prove that it is equal to left-hand side. Because we forgot, we didn't take the right-hand side. Same things can happen. We had to always think, we wanted to show that this goes to 0. This is the difference between the two solutions, started at various points. And here is what I say, what I get, and I'll do the following. This t, if I want to put it here, what should I do here? The t was only here, so I had divide by t, right? Okay. And for some reason, let's say I want to also put a nu here, in which case I should put a nu squared. Don't ask me why. Now I will consider this part. Okay. I had to go to the energy inequality and then once again estimate this.
And show that
Exactly.
quotient is bounded by the
That's right. But there is a catch, namely there is also a stochastic term, right? Okay. So let's go once again to the energy equality. V0 square. Oh, as you well know, I like to write things on this side, right? Nu times integral 0 to t 2 nu. And then there is the V of s square ds. We are almost there. And what happens to the inertial term? V of v acting on v itself, correct? V of s, V of s. And this is equal to what? V of 0 square plus integral of sigma j wj of s with v here, summation 0 to t. So where is this norm? A norm of v squared with a nu and so on. It's right here. Did I put everything else correctly? There is a 2. There is probably also a 2 there, but it doesn't matter one bit. And then here I have a 2. Huh?
First term on the left hand side.
First term on the left hand side is t. Correct. Very good. What else is there? Any other term missing? So this is not the energy. See, if I write just this much, then it is the energy equality corresponding to ODEs and so on, right? Or PDEs. There is an extra term. And what is the extra term? 1/2 and 2 will cancel out, and then I'll get integral 0 to t summation what? Sigma j squared ds or something like that, right? You all agree with this? Okay. So now you just divide by t everywhere. So isolate this and divide by t. Divide by t. So if I get, I can even drop this term, all right? And I have this, this is what I want to prove about. So I have nu times integral 0 to t norm v squared, and let me divide it by t. That's going to be less than or equal to, I have to divide here by t, here by t, and here by t. But summation of sigma j squared, what did I say? It's bounded by a constant and so on. So it just, when I divide by t, I cannot still say it goes to 0, right? It's still there, okay. It is less than or equal to, okay, let me, what about this term? Are you all, it becomes 0, right? Because it is b of v, v, v. If the last two are 0, then it becomes 0. So this is gone. I have v of 0 squared. Okay. Divided by t plus I have the martingale divided by t plus I have the summation of sigma j squared, sigma j of s squared ds, correct? Okay, so what should we do now? I got to tell you that this goes to 0 as t goes to infinity. It's all almost sure, right? I may have to change there some of these things. And how about this? Okay, now let's look at the martingale part. It is summation of what? Integral 0 to t, sigma j comma v, right? One to infinity. Take the bracket process, variance of this. I'll just say quickly. I have written something else in my notes, and then the wj's are all independent. Therefore, it would just become 0 to t of sigma j v. Everything depends on s. Okay, squared ds. Expectations there, which is less than or equal to summation j varying from 1 to infinity of expectation integral 0 to t sigma j squared and then v of s squared ds. From the a priori estimates, you can prove that the expectation of v s squared is bounded by a constant. All right. Therefore, and the summation of sigma j squared is also bounded by a constant, right? Because that's what we got it. So anyway, this is all less than or equal to some c star or whatever, some other constant times t. If the variance of a martingale just grows like t, then you can rest assured that the martingale divided by t would go to 0. Almost. Why? Because take the case of a Brownian motion, for instance. Okay. And the Brownian motion divided by square root of t, for instance, that would stabilize it actually. Then it becomes a normal variable, normal 0, 1, right? If you put any higher power, it will go to 0 almost surely. All right? So the only thing that it can withstand is by the law of iterated logarithm, that it would go to a non-zero number. But if you take anything higher than that, it will grow like t log t, right? But anything more than that, it will go to 0. So here it goes to 0, no problem. Right? It is in this way that we show that the terms and all go to 0, and we want to make this as a negative number, right? So here is a summation of sigma j squared L, right? And what else do we do? Let me see. It is just the conditions are to ensure that what we put here is whatever stands here is that this